Welcome you folks in the last session of the module 2 lectures. That is, today we talk about the interconnections of more than one subnetworks to establish a complete network, or you can say that whenever you have a complex network or complex systems, so typically those complex systems are nothing but it is a group or combination or myriad of number of devices or circuits. Okay, or even if you have a complex circuit itself, that complex circuit can also be simplified using number of small networks, or you can say that sub networks, and establishing an interconnection among all those sub networks in serially or in parallel manner, so that you can have got a complete one integrated network. Okay, so that is the objective, that how today we will discuss that you can use a particular type of parameters or their quantities to establish a interrelation among the networks. Okay, so that the flow of power or the flow of energy or flow of current could occur in a particular direction and in a particular graded fashion or the step fashion. Okay, so that means we are talking about serial to serial, parallel to parallel, serial to parallel, or parallel to serial communication. Okay, so here I communication means to say that the interconnection among the networks. Okay, that is so that the flow of information, the flow of information, or the flow of signal, flow of function should occur without any interruption. Okay, so as far as any typical two-port network are concerned, it can be typically connected, okay, as a in a serial manner or in a cascade manner. You can say that technically both are same, or in a parallel manner. Okay, so if you are talk about these two possibilities, obviously 2 raised to 2, you might have a maximum get 4 or different possibilities. One, the serial in and serial out. That means what? The electrical variables, whether the voltages or currents, okay, are available in form of the serial input, okay, or they can access to this network in serial manner only. Okay, similarly, the access to the output port variables, voltages and current, are available in serial manner only. Or you can say that the output current and voltages, which those that are feeding to the network, is established or is interconnected in serial manner only. So both the side of coin. Okay, if it is so, if that means the input mode is available in serial mode and the output mode is also available in the serial mode. So it is called serial input, serial output. So therefore, in such case, it is advised that you should prefer the Z parameters. Okay, to do or to interconnect the relation between the networks. Okay, to establish the interconnection between the networks or among the networks. Okay, similarly, if you will go for, if serial input, serial output is meant for Z parameter, then what is parallel in and parallel out? Obviously, it is the complement of each other. So in that case, we prefer to go for Y parameter. Sometimes it is also called the shunt input, shunt output, but the typical more popular is parallel input, parallel output. But in the remaining two, and as I in the beginning of the last lecture, I told you that whenever there is a serial input and parallel output kind of interconnection, you should always prefer the H parameter. Why? Because the input mode of the H parameter is favoring to the interconnections of the is arranged in such a way that it is duplicating the arrangement of the Z parameter, whereas the output port module of any H parameter or any transistor or any electronic device is copycat to the Y parameters network structure. So the output is available in parallel form, that means in shunt mode, where the feeding of the current and voltages in this input mode is available in the serial form. So it is serial to parallel interconnection. So if H parameter is suited for serial to parallel interaction, serial input and parallel output. So what about the G, which is the inverse of it? So it is the reverse, parallel input and serial output. Okay, you see this particular diagram where you have four different possibilities, which shows that how the individual quantities of the two-port network are interconnecting with each other. Okay, for the sake of better understanding and the easiness, okay, to evaluate, we consider only two networks only. Practically it can be two or more than two. Okay, so in each case we consider the two networks, okay, two individual networks to form a an to form an interconnected network, to establish an interconnected network. In that case, you see that how the serial and parallel interconnection to the individual networks will help you to analyze the system or to interconnect the network using one of the parameters or quantity domain. Okay, see it, and then we continue our discussion. So as you can see that if you are going to consider this first figure, so in this case you can see, you can appreciate that if you are going to write down a standard Z parameter two port equations, what is it? It is, so for example, you have two networks. So we will say that for Z1 it is, yes, for the Z1 it is V1 is equal to, so rather than V1, because now you have the two different terms, so we will write V11 and V12. So remember, this V12 is doesn't means in the backward direction. Okay, this is subscripting. V1 is the input, okay, and 1 is relating, or 2 is relating to that particular domain. Okay, so it is the Z1 subnetwork. So from here it is coming 1. So, okay, so it is V2 is the output. Again, for V2 is the output port. So though it is V2 of the one network or V2 of the second network. Okay, so that is it. Okay, so you should not be confused. So we are connecting it. So because you are, how the interconnection of the Z parameters we do, that is V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z21 I1 plus Z22 V2. So you know that whenever the voltage is a dependent source, then the voltage is always added, okay, in serial manner, right? So that's why we are going to connect a cascade interconnection here. So you see the same amount of voltage V1 is available over here and is available over here. So it is a cascade combinations. Fine. Similarly, if you talk about V2, it is this domain is also connected. These two networks Z1 and Z2 are also again interconnected in the serial manner. So because of that, what happened, that V2 will be available over here and available here. So overall V2 is the sum of V2 1 and V2 2, right? Similarly, overall V1 is equal to sum of V1 1 and V1 2. So whenever there is a serial input and serial output interconnection, you should use Z parameter analogy to interconnect this particular network. Okay. Similarly, if you see the Y parameter, you see here the devices are connected in shunt. Okay. Both the network, if you can visualize in terms of the three dimension, in that case you will see that this Y1, whole Y1 is in parallel to Y2. Okay, this is a Y1, I'm sorry, and this is Y2. But anyway, okay, any one of the network is 1 or 2, it is immaterial. So 1 is in parallel to 2. So you can see that, you can appreciate that V1, Y1 is somewhere here, and adjacent to this, then Y2 is somewhere here behind to that. Fine. So the, in that case you can say that the common voltage is available. Okay, the common voltage is available here, but the current being added, because the amount of current which will penetrate through this V1, certain amount of current will pass to Y1. So let's say this part is I11 and this part which is passing parallel to Y2 is I12. So this total I1 is equal to I11 plus I12. Similarly for I2, it is I21 and I22. Fine. So the current is actually dividing or adding. So that means the both the networks are interconnected in parallel, and you know that admittance can be directly added in parallel. Okay, just like impedance can be added in serial. Okay, in series. So similar admittance can be added in parallel mode. Fine. So your Y is equal to Y1 plus Y2. That is the reason you are getting. So therefore, whenever you have a two networks, those are interconnected in parallel mode, you should use Y parameter for analyzing the things. Okay, the numerable examples you can get that. Similarly, you will appreciate that you can get the serial. You see that this side input side is the voltage input, this side is the current, is the analogy. So here the parallel mode is available, port number 2, the port number 1 is connected in a serial mode. So this is serial to parallel interconnection. G is parallel to serial interconnection. That is the reverse of the H parameter. Okay, so I hope that you appreciate it. Even for a little better understanding, again, this is the different way of interconnection is given. Again, in the last lecture I have told you that as far as the cascade connection is concerned, okay, both are basically primarily in principle is getting the summation of the things, but what difference you will get when you talk about series interconnection. So this is how exactly you got the series interconnection. When you talk about cascade, when that was adjacent to one to another, okay, one to another, adjacent of one to another. So in that case, if there is a cascade combination, okay, just like we can see in the T network or the transmission network, then we use the T protocol, T parameters, okay, or the quantities of the transmission parameter to establish the relation between the two network or more than two networks. Then I'm going to write down as three standard equations, three mass equations or the three nodal equations, and you will be able to do a lot of interconnections, okay, exchange of the variables, interpolation of the variables, and then you are getting your, will be supposed to get reach your conclusion. Another way, the smarter way, that as I told you, that you assume that there is a one block of a network N1, which is a T network, and there is another block is network is N2, and then these two networks are parallelly connected with one another. So how simple it is. Now you can very easily calculate the impedances or admittance, whatever you are asked to calculate, because this is a T network. So very easily you can calculate your impedance parameters if it is asked for that. If it is asked for Y parameters, so still you can work out as, but like in the previous lectures, I advise you that whenever you want to calculate the Y parameters, it is always suggested to convert your T or star network into the delta or pi network, and then you calculate it. But here our job is to calculate the Z parameters. So you can say that this Z parameter is a single element. Okay, so you can calculate the value of N1 and N2 both individually in terms of Z11, 12, 21 and 22, and then later on what you can do, that you can establish a parallel combination if you are wanted to work out the Z parameter. If it is a Y parameter, then you can simply add it. Okay, so I hope that this idea is clear to you. Okay, as in this demonstration you could see. Okay, so from your network N1 and N2, okay, and then it is going to converge into the Y parameters. Okay, so that is one way. Fine. Another is that you take the parallel network, directly convert to the pi network, and straight away you get the Y11, Y12, Y21, and Y22. Don't require to calculate the Z parameters. Okay, do adopt the most smarter way, and the smarter way is that your solution is smart enough if it is consuming least amount of step without violating any constraint or any conditions to reach to the conclusion. Okay, so that is the best algorithm. Okay, the least the number of steps you will take in mathematical modeling, faster your evaluation is as far as your computation timing is concerned, or your response time is concerned. Lesser will be your response time. Okay, and that will be the most optimal solution. Right? Okay. Y parameter in terms of the Bristol networks. So I hope that you got it. Right? Interconnection of the networks. You see this particular diagram, what I have told you about 4 or 5 slides back. Okay, and here probably with the help of this diagram, you will be able to appreciate more easily. So as you can see that to establish this particular whole as a one single integrated network, it is nothing but it is a combination of two networks N1 and N2. And if you see the input side, the interconnection between the two networks are connected in serial manner. Here over you can see. Okay, so the current is flowing, is the amount of current is flow is the same, whereas as far as that your v1 is concerned, so this particular v is additive over here, v1a plus sum of v1b, which is equal to v1. Similarly there is a serial interconnection between v2. So in this particular diagram, that's how you can assume your nomenclature during the calculation. So that will help you to ease down your job, do the individual calculations, individual analysis for the individual networks, and then later on, because you see that if the serial mode and parallel mode are the interconnected, in that case you just sum up those domain terms, because you know the for the serial network current is the common and voltage is the additive, so you have to do that job. So that's how you can establish that you can solve the individual networks, the smaller network, simpler network first, and then you add in terms of response. So ultimately, because it is connected in serial, so therefore your ZA plus ZB is equal to ZA is the impedance of the parameters of the network NA, and ZB is the impedance parameter of the network NB. So overall Z will be the sum of ZA plus ZB. So as you can see in this particular problem, typical problem where you see that the source voltage and the V1, okay, as far as the V1 is concerned in node, I would say that 1 dash, okay, this box, this white box where the value of Z11 is 12 ohm resistance, Z12 is 8 ohm resistance, Z2 is 8 ohm resistance, and Z22 is 20 ohm resistance respectively, are creating as a whole one network. Let's say for example that is network N1, and in parallel to that, okay, in cascade to that, this 10 ohm resistance you treat is not the part of the whole but as an individual network. So let's say N2 is equal to this 10 ohm network only. Okay, so in that case N1 and the N2, which is a 10 ohm resistance, are connected in cascade from both the sides, sorry, in the series in both the sides. Okay, so in that way, but remember that keep this 20 ohm resistance as out of the network because it is nothing but it is a load resistance. Similarly, this 5 ohm resistance but nothing but it is showing the significant resistance between the voltage source and the node voltage, that is the across the node 1 dash, okay, across the terminal 1 dash I would say. So there is difference between V1 and Vs through this 5 ohm resistance. So keep 5 ohm and 20 ohm resistance separates, and then you are able to attempt this particular problem so that you can simplify the network and you can easily get the answer, you can easily analyze the networks. Okay, so do it. Fine. So in that case, one network is NB, which is recognized in that way, and there is another network ZA, which component is already given. So you can add these two components, and then therefore you will be able to get the overall Z, which is 22, 18, 18, and 30. So it's nothing but it's an example of reciprocal network. The interconnection is establishing a reciprocal network. Once you got that, and then at the input port, you know V1 is equal to, there is a separate 5 ohm resistance from the source voltage, so it is Vs minus 5 I1, whereas the V2 is equal to minus of 20 I2. So from there you can get the value of I2. Okay, and you can substitute the value of I2 in terms of V2, because remember your ultimate goal is to get the ratio or the interrelation between source voltage and the output voltage. Okay, so that's why we are doing all this exercise, this permutation combination, so that ultimately you can get the value of Vs in terms of V2, which is now is 2.85. So V2 by Vs will be 1 upon this, so roughly around 0.35. So, okay, so that's how you can get your analysis done. So exactly the same exercise and the similar kind of practices you can also repeat for the parallel networks, for the serial to parallel network and parallel to serial network. Ample amount of problems are given in both the books, or even you can pick any other books also, Head or any other book you can refer, whatever you comfortable, and then you try to analyze the component, try to practice those problems. If you face any difficulties, so obviously in the beginning of the next module, number 3, the initial 5 to 10 minutes of time I will allocate specifically for your doubt clearing session, and there you can pick up your problems, we can discuss one by one, and then we will move ahead. Okay, so as you see that at a certain level, how the individual parameters, okay, depending on the constraints applied by the current in terms of voltage or current, that is the open circuit condition or short circuit condition, okay, and also looking into the interconnection of the network, that means the serial communication interconnection, parallel interconnection, or cascade interconnections, you can decide that which particular quantity or which particular parametric approach will be analogy will be suitable to model and analyze the particular given network. Okay, so that's what we learn from here. Now under the head of network function, we don't bother about the internal configurations. Now we are going to completely study the overall network as a single whole system. Okay, so remember, as far as the network function is concerned, the analogy adopted in the Abby van Valkenburg is quite different than the other book. So please be noted this, what the nomenclature we are using in Abby van Valkenburg is outrightly different, way different than that of the Boylsted, Head, or any other Indian author books. Okay, so in that particular case, so in the next module, whatever I am going to refer you, that content I am going to refer from the network functions of mostly I think it's the chapter number 10 of the ME Van Valkenburg. Okay, with this, I'm ending up this lecture series, and in the next lecture, we are going to meet for the module number 3. Thank you.